So now that we've gone over how to do a derivative, how to do an integral, it's time to put this together with vectors. So remember, if we write the position r of t, it's a vector. So it has some x component, some y component, and some t component. So we said that velocity v is dr dt. So what that means for the vector components is this is just dx dt, dy dt, ez dt. Remembering this is, another way to write this is, vx, x hat, plus vy, y hat, plus vz, z hat, where we just remember, vx is dx dt, vy is dy dt, vz is dz dt. And then similarly, acceleration is dv dt. So this is the second derivative of x with respect to t squared. Second derivative of y with respect to t squared. Second derivative of z with respect to t squared. So the acceleration, is just a change in velocity with respect to time. We'll talk a little bit more about that in more detail when we go into, when we get into the next book, into Newton's equations. So for now, that's what you need to know about the acceleration. Velocity is derivative of position with respect to time. Acceleration is derivative of velocity with respect to time. So when you're taking the derivative of a vector, you're taking the derivative of each component. So if you had some other kind of vector, we'll call it q, and we'll just say, this is q1, q2, all the way through qn. dq dt would just be dq1 dt, dq2 dt, all the way down to dqn dt. Okay, so that's the only thing we're really adding now, is we're saying, remember how you did a normal derivative, but now you need to do that on each component of the vector. And in the next video we'll see why that's important.